Okay, so next we will learn about the nucleophilic substitution in halogenoalkanes known as SN1 and SN2. Okay, you should understand what is SN1 and SN2 because yeah, this type of reactions is very often appear in the questions. Okay, you know that halogenoalkane once again has the positive partial region and the negative partial region due to the presence of electronegative atom Cl. Okay, because of this positive and negative partial charge, this will attract a component called as nucleophile to attack this carbon, this positive carbon. Why? Once again, nucleophile is an electron-rich species. Electron-rich has lone pair that try to attack a positive region. Okay, so because of nucleophile attack this, and then later on the Cl will be released by this compound. This is called as nucleophilic substitution. Okay, nucleophilic substitution. So that's why it is not, for example, an electrophilic substitution. You know why? Because the species that attack this positive region is a species that has lone pair. Let's say this, and this is not electrophile, but this is nucleophile. So that's why it is not called electrophilic substitution, but nucleophilic substitution. Okay, we will learn about 4 types of nucleophile, in these nucleophilic substitution reactions. Those are OH minus, from dilute NaOH, nitrile, Cn minus, ammonia, NH3, and H2O. Please remember that primary halogenoalkanes react by SN2, while tertiary will react by SN1 mechanism. Okay, this is the general mechanism of nucleophilic substitution. The lone pairs from the nucleophile will attack the positive region of halogenoalkane, which is the C, connected directly with X. Okay, and then the CX bond will be break, to release the X minus. Okay, we call the X minus as leaving group because it leaves the halogenoalkane molecule. Okay, if the CX bond is very easy to break, then the reactions will be occur in a faster rate. Okay, so later on you will see that if X is iodine, it can react faster compared than if X is chlorine or bromine, example. So what's the product for nucleophilic substitution of halogenoalkane with OH minus? It is a new compound that called as alcohol. Okay, so this is the way of how to produce alcohol from halogenoalkane. Okay, this is the general mechanism, but now we want to learn about the SN1 and SN2 reaction. Okay, we will start from SN2. What SN2 stand for? This is nucleophilic, and then S is for substitution. Nucleophilic substitution 2 because bimolecular. So SN2 is nucleophilic substitution bimolecular. Okay, why it is called bimolecular? Because in the red determining state, yeah, in the red determining state, two molecules affect the red, yeah. So red equals to K, this is the red constant, times concentration of halogenoalkane times the concentration of the nucleophile. So once again, this is called as bimolecular due to two molecules affect the red of reaction. That means the halogenoalkane and nucleophile both affect the red. Yeah, if you change the concentrations of nucleophile, for example, the red will be affected. If you change the concentration of Rx, halogenoalkane, the red will be affected as well. So that's why this is called as nucleophilic substitution bimolecular. In this mechanism, the OH minus will attack the C positive. Once again, you should understand which one carbon that has positive partial charge. Not this carbon, right? Since this carbon is not connected to halogen. So please be careful. Yeah. OH minus will attack the C positive. Give the curly arrow to show this, the lone pair to the C positive. Okay, as the incoming group, we call the nucleophile as incoming group, yeah. As the incoming group attack the C positive, the CX bond will be break. Okay, before it break, before the new bonds form and the CX bond break, it creates a condition that we call as transition state, which is a pentavalent carbon. In this transition state, carbon has 5 hands. You can see here, this 1, 1, 2, 3, 4, 5. So that's why it is called as pentavalent carbon. And you can see here, it has a negative partial, a negative charge, yeah, due to OH minus attack this molecule. So now this transition state species has negative charge. Okay, and this is not stable. Why? Once again, carbon will not have 5 hands, but only 4. So that's why it is unstable. Okay, according to the energetics, you know that if the reactions provide enough energy and it reaches the activation energy, then the product will be occur. Okay, the product occur and alcohol will be formed here. Okay, understand? Okay, now I'd like you to see about slow and fast here. Okay, the process in which OH minus attacks C and then the CX bond break, this is a slower step, yeah, for this reaction, slow step, because it require a very high amount of energy. This is, it is called as activation energy. Okay, so if you want to draw the diagram, energy diagram, okay, so let's say this is an exothermic reaction. Okay, this is the step where the pentavalent carbon occur. Okay, this, and if it has enough energy, the product will be formed. Okay, so once again, this is the, yeah, the slower step. So you can see that at the slower step, OH minus and Rx present, right? OH minus and Rx present in the slower step. So that's why it is called as bimolecular reaction. Okay, for the second step, it is fast. Yeah, if the transition state already achieved, then the product will be produced at the faster rate compared than the first one. Okay. Okay, understand? Okay, and then the second thing that you can see here about the position of nucleophile. Nucleophile attack the C positive, yeah, from back. I mean, if we have a Cl1 here, the OH minus will not attack from here at the same position, will not. Okay, this is wrong. Yeah, but OH minus will try to attack from the back from the position of Cl. Okay, why? Because Cl is a quite large atom, and also OH minus is also large. So large group cannot attach the C positive if the surrounding causes a very large group as well. So OH minus will try to reach a C positive. Yeah, OH minus will try to reach C positive when hydrogen atom bonded to the C. Yeah, I mean this is large group, CS3 large group, Cl large group. So it try to find the position of each. You understand? Because it is very small, so it has a large space to reach the C positive. This phenomenon called steric, yeah, steric hindrance, yeah, where the large group, yeah, prevent the position of an atom, yeah, to attack by another groups. Okay, in this case, once again, CS3 large, Cl large, so that's why OH minus cannot attack C positive from this position. Okay, so that's why it tried to find the position from back. Okay, and then you can see as well the product is very interesting. Why? Because it has the inversion configuration. So you can see that before in the two-dimensional image, the CS3 is at this position, right? So you can see that this is yeah, the position is more to the left, right? But you can see after the nucleophilic substitutions occur, you can see that CS3 is and is more to the right side, right? So this is called as inversion configuration. Yeah, because O is minus, yeah, attack from back. Yeah. So this is like if you open the umbrella and a very strong wind, yeah, yeah, attack from this side. So this makes your umbrella position will be like this, yeah, and your umbrella position like this. Okay, so why it has the inversion configuration? Yeah, because of O is minus, yeah, attack at this position. Okay, so these three groups will be inverted to this side. Okay, let's see once again about SN2. Once again, is it clear? Okay, one more. Please see this title, Primary Halogenoalkane SN2 Mechanism. The question is why it should be primary halogenoalkane that undergo SN2. How if we have tertiary CS3 around 3CS3 around Cl, for example? Can it undergo SN2 mechanism? Okay, once again, this is about steric hindrance. You can see that CS3 is the large group, Cl, CS3, CS3. There are many large groups, yeah, at the surrounding of C positive. So there is no way for OH minus to reach this C. Okay. Okay, if you draw not in a condensed structure, you can see what I mean. Yeah. Okay. Very bulky, right? No space. No space for OH minus to reach this C positive. Okay. So if you compare with primary, yeah, CS3 CCl, CS3 CS2 Cl, you can see that there are two hydrogen atoms which is small. So this open, yeah, for the OH minus to attack this C. So that's why SN2 mechanism occur in primary, not in tertiary halogenoalkane. This is due to steric hindrance. Yeah, no space to attack the C positive in tertiary halogenoalkane if it is undergo SN2 mechanism. So the question is, so how the nucleophilic substitutions of tertiary halogenoalkane occur? Okay, it will use the another mechanism later on. Okay, let's practice about SN2 first. Try this. Okay, let's answer this question. Okay, you should draw the mechanism. Look, if you see the word mechanism, that means you should show how the electron moves by a sign with curly arrow. Okay, once again, every time you see mechanism. So first, you should draw the chloropropane once again. Yeah, CS3, CS2, CS2Cl. But because you should show about the how the nucleophile attack the C positive, so this is not a good representation. Okay, so you should change this diagram, this image, by show how the CCl bond appear, yeah, in this compound, and then this is our center, yeah. Okay, and then we have CS2CH3 here. Okay, and then there are 2H here. Okay, and then please show the alkali. Alkali, that means give you OH minus. Okay, and then draw the curly arrow from the nucleophile to the C positive, and then the C heterolytic fission between the CX bond. Once again, this is the slow step. Okay, slow step, and it will create the pentavalent carbon first. Pentavalent carbon is when the incoming group and the leaving group, yeah, attached to the same carbon. Okay, it has negative charge since OH minus attack, yeah, attack the chloroalkane. And then this is fast. Yeah, that's when the CCl bond break, so to form the product. This is CS2CS3, yeah. CS2CS3, HH. Okay. So this is how the mechanism of SN2 reactions from primary halogenoalkane with alkali. Okay. What's the name for the product? Can you give name? Okay, this is alcohol, right? Since it has OH group, the carbon attached to alcohol should have the lowest number. So you can see that this is propane 1-ol, yeah. Okay. Once again, the question is how the tertiary halogenoalkane undergo nucleophilic substitution. Since once again the steric hindrance occur around the C positive, the nucleophile cannot reach the C positive. So how it can react through nucleophilic substitution mechanism? Yeah, it will react through another mechanism, not SN2, but now we want to learn about SN1 mechanism. In SN1 mechanism, the tertiary halogenoalkane will break the CX bond at the first step, and this is very slow. So this is the rate determining step in this reaction. You can see at this rate determining step, OH minus does not present, right? Only the halogenoalkane, Rx. So this rate of reactions depends only from one compound, which is the halogenoalkane concentration. Okay, so that's why it is called as unimolecular reaction. Unimolecule because of only concentrations of halogenoalkane present in the rate determining step. Okay, so the rate equals to K times concentration halogenoalkane. Unimolecular. So SN1 is for nucleophilic substitution unimolecular. Okay. Okay, so the slowest step is when the CX bond break. What the product if the CX bond finally break? It will change to carbocation intermediate. Okay, because the electrons, the shared electrons goes to Cl to form Cl minus, heterolytic fission to form positive carbocation and Cl minus. Okay, you know that the positive carbocation has the planar structure. Yeah, since once again it has only 3 hands here, 3 hands. So this is an sp2 carbon, and you know that sp2 carbon has a trigonal planar shape, right? Okay, you can imagine like this. Okay, this is planar. So later on, the OH minus can attack from above or from below. Okay, because it is very open. Yeah, very open. The position is very open since it is planar. Planar, okay? No steric hindrance occur. Yeah, because it is already changed to sp2 carbon. Okay, so if the nucleophile already attack this carbocation, yeah, this will form the product. Okay, the product is 50%. 50% of OS minus attacked by the above position, and then 50% from the below position. So we call this as racemic mixture. Okay, not inversion, but racemic mixture. So once again, 50% nucleophile, the product produced because of OS minus attack from the above position, and 50% from the below position. Okay. Okay, I hope you already understand about racemic mixture. Those will not rotate the polarimeter, yeah, since yeah, they cancel out, yeah, the rotation cancel out. You have learned about this when we discuss about optical isomerism. So why primary halogenoalkanes not undergo SN1 mechanism? Okay, why it is only in tertiary? Can you imagine if the primary halogenoalkane undergo SN1? Let us draw the primary halogenoalkane. CH3, C, Cl, HH, yeah. This is primary halogenoalkane. If it undergo SN1, so it will produce this carbocation, right? This carbocation, right? Okay, if you compare the carbocation produced by the tertiary with carbocation produced from the primary, it is clear that the stability very different, right? Yeah, since this is a tertiary carbocation, and this is primary carbocation. The stability is very different since the tertiary has 3 R groups. Look here, 1, 2, 3. You can see that it pushes electrons towards C positive. It tried to spread out the positive charge of C. Hence, it helped to stabilize this carbocation, right? Through the positive inductive effect. But in primary carbocation, we just see 1 R group that try to stabilize this C positive. So, the stabilization of primary carbocation is less compared than the tertiary. So that's why the primary halogenoalkane tend not to undergo SN1 mechanism, but SN2. Okay? Okay, understand? How about secondary halogenoalkanes? Okay, the secondary halogenoalkanes will, for example, this, yeah, Cl, C, C, C. Yeah, attached to 2 R groups. How about this? Yeah, SN1 and SN2 mechanism are both likely to play a part in the nucleophilic substitution of secondary. Okay, so secondary can use SN1 or SN2 reaction. Okay. Okay, this is the final summarize of SN2, SN1. Okay, so SN2 has the red equation. Red equals to K times Rx concentration times nucleophile concentration. Yeah, 2 molecules, 2 substances, so SN2. While SN1 only the concentrations of Rx. The stereochemistry is inversion product or stereospecific. And this is loss of stereochemistry. Yeah, racemic mixture. I said that there is no isomerism later on. Okay, the substrate for SN2 is the primary halogenoalkane, mostly, yeah. For SN1 is tertiary. Okay, the nucleophile for SN2 is strong or moderate required. Why? Because it should attack the C positive from back, right? So a strong or moderate nucleophile required. But for SN1, it's not important. The strength of nucleophile is not important since, once again, the rate of reactions only depends on the concentrations of Rx, not the nucleophile. For SN2, the leaving group is moderately important, moderately. Okay, so because you know that the transition state is pentavalent carbon, right? So if you have a leaving group, a good leaving group, it is okay, yeah. But if it is not, yeah, it's okay as well. But the moderately important is the moderately leaving group is quite important for SN2. But for SN1, this is very important. Why? Because the rate determining step, which is the slowest step of the reaction, it depends on how the CX bond break, right? This is the slowest step to form the carbocation for SN1 reaction. So the good leaving group is very important. Yeah, I is very good compared than bromine. Bromine better compared than the Cl. Okay, so the good leaving group is very important. The good leaving groups can be obtained if the CX bond longer. Okay, let's see the solvent for SN2 is polar aprotic, while SN1 is polar protic. Polar, that means there is an electronegativity difference. protic. Protic, that means can release proton, yeah, such as acid, yeah, or water, yeah. So polar protic. But polar aprotic, that means polar but cannot release proton. So for example, propanol, yeah, this is polar but cannot produce H plus, cannot produce proton, right? So this is solvent for SN2 region, okay? But for SN1, polar protic. Why should be polar protic? Because the polar protic solvent needs to stabilize the carbocation, yeah, that formed during SN1 mechanism, okay? While in SN2, there is no carbocation formed, so no need to stabilize with use polar protic solvent. So polar aprotic is good for SN2. Okay, this is the energy diagram for SN1 versus SN2. For SN2, we already know that the pentavalent carbon transition state is at the top, yeah, of the energy diagram. But for SN1, you can see that there are two peaks here. Okay, the first peak is for when the Cl bond, yeah, the CX bond break. Okay, so let's say the red determining step here, yeah, is when the CCCX bond break. Yeah, this is the conditions when it is at this top, this position. Okay, after the CX bond release, it formed the carbocation, right? So this position is for, sorry, yeah, for this. Yeah, for this attacked by nucleophile. So R positive plus X minus, yeah, plus nucleophile here. So this is at this position. Okay, at this position is when the nucleophile make bonds, yeah, with the carbocation. Yeah, if it provides the energy and it is enough, yeah, then the product will be formed. Okay, so that's why there are two peaks, yeah, for SN1 diagram, while only one peak in SN2 diagram. Okay, you can see that the first peak is higher compared than the second one. So this is we call as rate limiting transition step or rate determining step here. Okay, because the highest energy.